Hi, everyone. Today we are going to discuss gyroscopes briefly. There are a lot of YouTube videos out there that have really good explanations about how gyroscopes work. So I'm going to post some links and recommendations in the comments. But we're going to go over a little bit about the physics of gyroscopes and how they can precess without falling, and how sometimes it looks like they're just completely ignoring gravity, right? So first, we can talk about gyroscopes precessing without falling. Precessing is when they start to wobble, but they can just wobble forever. They don't actually start to lose that much energy unless there is a frictionful environment. So it asks, which forces create torque on a spinning top? Is it the normal force, the ground pushing on it as it's tilted, or is it gravity trying to pull it down? So as we look over here, right, we can see that this image has a notation saying that the right-hand rule indicates that torque equals R cross F, which in this case would be R equals mg in the XY plane. So you can see here, you have R right there and mg right there. Those two vectors are what's causing the torque. The reason normal force does not cause torque on this top is because it's not a radius away from the axis of rotation. If this object were to fall, it would rotate about the axis of its point, right? Let me grab a gyroscope for an example. So if you were to watch this gyroscope fall, right, it would fall about this point down here, about the point it's making contact with the surface, right? So that we could see that as a rotation. Now, if torque were going to create that rotation, that normal force would have to be a radius away from the axis. Since it's not, that normal force is not going to cause torque about that point, which means that mg is going to create the torque. Okay, so the gravitational force, that is what causes our torque. Now for number 2, what does the net torque do to the top when it is spinning? Okay. So here, what the net torque is doing to this top is it's changing the angular momentum. However, it doesn't just change the vector in any specific way. It's going to change the angular momentum vector in a very important way. And that is because the angular momentum is going to only be changed by its direction. So, for example, okay, say you have a velocity vector, okay, and then you have an acceleration vector pulling down on the object. Well, since this is at a 90-degree angle, we know exactly what's going to take place here. This velocity is not going to get any weaker if that's the only acceleration involved. It's only going to change direction. And we know that because this diagram is what gives birth to circular motion, right? If that acceleration is always at a 90-degree angle, okay, because that acceleration, okay, acceleration means the change of velocity over time, right? It's going to change that velocity over time, but vectors have two things you can change: the magnitude, meaning the strength or the weakness, and the direction. So if that acceleration vector is always 90 degrees to the velocity vector, it's only ever going to change the direction and it won't affect the magnitude. Now, let's talk about angular momentum again. Say your angular momentum is purely in the j direction, okay? But you have torque purely in the I direction, okay? That means that since they are at a right angle, that your torque will only ever cause the angular momentum to change its direction. It will not change its velocity. Now, for it to change its velocity, that is possible. Okay? Say you have your same angular momentum in the j direction. However, now we have torque that is ever so slightly in the I direction and in the j direction. It also has a j component because of this angle theta. Okay? Here would be your torque component in the j direction. Okay? Now, since there is a j component and there is a j component for the angular momentum, that means that your torque will now act on that j component because, like when acceleration equals the change in velocity, torque equals the change in angular momentum over time, right? Now, if that torque were to have a j component in common in the same direction as the angular momentum, instead of in the opposite direction, that means that that torque would now cause an increase in angular momentum, whereas the red vector would have a decrease in the angular momentum because it's actually affecting the magnitude. But this is what happens for a gyroscope. You have the angular momentum coming out the top of the gyroscope. That is because, right here, okay, because of the nature of angular momentum, right? You can follow the right-hand rule to show that wherever your I omega is, right? When you have I and omega, wherever your omega is turning, your angular momentum will be along the axis of rotation. Okay? But the torque isn't going to be in that direction. The torque is actually going to be at a 90-degree angle to that angular momentum. And because of that, it's not going to change the magnitude of the angular momentum. It's only going to change the direction, which means that your top is actually going to make this kind of motion. Okay, imagine this cone is the axis tracing the cone in space. Okay, and the only way that the magnitude of the angular momentum is going to change is due to friction, not due to gravity or due to torque. Now, getting a frictionless gyroscope is very expensive and very difficult. So all of them are going to have a little bit of friction, or some of them are going to have a lot. Like some of the ones that we use here, they're kind of old and they have a lot of friction. But the angular momentum only changes direction. It's not changing magnitude because the torque doesn't have a unit vector in the same dimension as the angular momentum because they're at a right angle. So that answers number 2. Number 3, why does the net torque do something different when the top isn't spinning? So we talked about how torque is the change in angular momentum, right? Now, angular momentum exists if something is spinning, okay, I omega. But if something is not spinning, it doesn't have angular momentum. So like we said, that torque, see, that torque wants to act about the origin, right? It wants to make the object fall over, okay? But it doesn't if it's spinning with enough angular momentum, right? If it doesn't have enough angular momentum, then it will just fall. But if you have enough angular momentum, it's just going to precess, right? It just starts precessing, and I'm forcing it to do that. You can even hear the friction in this gyroscope. However, if it is not spinning, then the torque is going to successfully cause it to fall. Now, we can't credit gravity on all of this, right? Because if this were only due to gravity, it would just fall straight down. Due to torque, it actually causes rotation. And remember, if we have, say, for this gyroscope, my radius is this way, gravity is this way, meaning that my torque is pointing back at me using the right-hand rule. Well, if torque is going to going to change the angular momentum, dl dt, in this direction, that means that it's going to increase the angular momentum, which means that it's going to actually generate an angular velocity in this direction, which is the fall, right? So the reason that net torque does something different when the top is not spinning is because there is no angular momentum to change. So then it must give angular momentum. And to do that, it causes rotation or angular velocity about the axis, which is that point of origin, right, from our picture, that the object is standing on. Now, number 4, how much work is done by the force of gravity during a complete cycle? So complete cycle would be this, right? a complete precession cycle? Now, the answer to this is 0. There is going to be 0 work done in this case. That is because there is no change in energy, right? Using the work kinetic energy theorem, we could say that if there is a change in kinetic energy, there is a change in work, or there is work involved. But here, there is no change in gravitational potential, right? So as that kinetic energy doesn't change magnitude, okay, and kinetic energy doesn't necessarily have direction, but as it starts going in a cycle, right? As it goes in a cycle, that work is going to show that there is 0 work done because it's returning back to the point that it was at, right? And we've talked before that when you have a perfect cycle, when something starts and ends at the same point without any loss of energy due to non-conservative forces, then there is no work done, right? And that is the same here. There is no work done on a precessing gyroscope because it is going to come back to its original point. Now, if that precession starts getting a little wobbly and it starts losing energy, that's work done, right? But we're talking about a perfect cycle. In a perfect cycle, no work is done. Now, we have 2 diagrams that I want to go over. The first one is the idea that this gyroscope is on a support, okay? This gyroscope is on a support in the diagram, right? Imagine it's my finger here, right? And what's happening is the gyroscope is starting to spin in this diagram, okay? Which can actually happen if I didn't have such friction-full gyroscopes. If you've ever seen the wheel trick, or if you look in our description, you can find YouTube videos that show where you can hold a wheel, and instead of the wheel falling, it will just precess. It will go in a circle about that point of origin. So that's what we have here. We have our point of origin, and we have our radius. Okay? Now, the blue arrow here, coming up from the origin, this would be a contact force that is supporting the gyroscope. This would be normal force. Okay? Now, the blue arrow down here, acting on the center of mass of the gyroscope, that would be mg. Okay? Now, these vectors coming out of the origin, okay? If we use our right-hand rule and we have Rm, okay, that's going to generate a torque not in the direction of those green arrows, so that can't be torque. What that is that is the right-hand rule looking at the angular velocity. Okay, if that gyroscope is rotating in this direction, the angular momentum would be along that green arrow. So this is our L initial, and this would be our L final. We can see that the angular momentum is moving in this gyroscope, and that is due to torque. Your torque is over here. And I will put my vector arrows over those there. Now that torque there is due because the radius is to the left, the mg is down, causing that torque to point towards you if you're doing that with me, right? So that's why the torque is coming out in that different dimension. Now, if we come over here, this shows the change in angular momentum. Here you have your initial and your final angular momentum, just like we had in the other image. But here it actually is trying to show us that there is a change in angle here, right? There is a d, they show d phi. I'm gonna use, well, now I'll keep it consistent, d phi, right? So that d phi is actually going to show that there is a change in angle as your angular momentum changes, okay? This green arrow here is the change in angular momentum. But notice that there is no change in magnitude between this and this arrow, okay? Their lengths don't change, only their direction. So that's why we can show that DL is perpendicular to these arrows, okay? And it's only changing the direction. You can also see that DL is parallel to torque. Now, it is in this diagram, it is not perfectly the same magnitude, right? Torque and DL have a different size of their arrow. However, if you increase the torque, you could also increase the DL. And if you decrease the torque, you could decrease the DL as well. So these are a couple diagrams of a gyroscope that can try and help you image or imagine this in a vector image. All right, next, let's talk about precession rate, torque, and rotational speed. So it says that using dl over dt equals the net torque and the vector diagram prove that the angular speed of precession omega p equals torque divided by angular momentum. And that's even in our image here. So we need to prove that. Okay? So using this image, we can see that there's a relationship between the change in angle and the change in angular momentum. And we have used this arc relationship before when we were talking about angular position, right? When you have an arc length S and a radius R, as that radius R changes direction via angle theta, that angle theta is equal to the arc length divided by the radius. Okay? That same relationship can be used for this diagram d theta. That would equal dl divided by the length of the L of the angular momentum vector. Now, we will start with this. I'm going to move this up to the top so I have more room to write. Now, we were asked to use this relationship, dl over dt equals torque. So if dl over dt equals the net torque on an object or on a system, that means that dl can be substituted for torque dt, right, by multiplying the dt over. So we can actually take this and substitute right in here. So that shows that d theta equals torque dt divided by the angular momentum. Now to give that d theta some meaning, let's divide the dt over. You have d theta divided by dt equals torque divided by angular momentum. And we know that d theta over dt equals omega. So that is where we get the idea that the omega of the precession equals the torque divided by the angular momentum. Okay? And that's how we can show that, by using the dl over dt equals torque relationship, and by using this concept that the angular momentum, the magnitude does not change, but the direction does in a gyroscope. And that's why we're using this precession omega in our answer. All right, last bit to talk about. Okay, questions to ask a gyroscope. So first, what does torque do and how does it affect a gyroscope? So a little bit of a summary. Okay, torque changes the angular momentum of an object or of a system. Okay, and how does this affect the gyroscope? Okay, so when the torque either changes the magnitude or the direction, or both, of the angular momentum, this is going to affect the gyroscope by moving the direction of its angular momentum vector, which can cause precession. If there is no angular momentum, then it will not move, then it will not precess, it will simply cause a new angular momentum to take place. Now the next question is, what is precession? So precession has a kind of complicated definition. It is the movement of a spinning body's axis of rotation but this movement of a spinning body's axis of rotation is about a separate axis of rotation. So that is the definition of precession that we are going to use. A spinning body's axis of rotation starts moving. So I'll show this with this gyroscope. Okay, I'm not going to actually have it do it itself because it has so much friction. But the axis of rotation here, okay, you can actually see that is actually the bar. right? So we have a visual representation of that. But when it starts precessing, right, that means the axis of rotation itself starts moving. And it starts moving about a separate axis of rotation. Okay? That is the definition of precession. Now, numbers 3 and 4. Does precession speed depend on the rotational speed of the gyroscope? So it actually does. We just defined that omega p equals torque divided by angular momentum. However, we know that angular momentum equals I omega, but that omega is the angular velocity of the gyroscope itself, which means that omega p has this inverse relationship. I'm going to use a squiggle instead of equal. It has an inverse relationship with the angular speed of the gyroscope, which means that as the gyroscope's angular speed increases, that's going to decrease the angular velocity of the precession, right? But as the gyroscope starts losing speed, it's going to start precessing faster and faster and faster until eventually it's going to fall, as you have probably seen with spinning tops before. This just puts it in math, right? So yes, the precession speed does depend on the rotational speed of the gyroscope. Number 4, last question, does the precession direction depend on the direction of the gyroscope's rotation? That it does also. If you have a gyroscope rotating counterclockwise, the precession will also go counterclockwise. And if your gyroscope is spinning clockwise, the precession will also go clockwise. And we can also see that here. Clockwise, angular velocity is positive, right? And clockwise would be a negative angular velocity. Well, since we have that relationship here, if this guy goes negative, so does the angular velocity of the precession. So the direction of that angular velocity does directly affect the direction of the precession's angular velocity because of that sign change. Now that is going to wrap up our chapter 11 videos. Okay, and then chapter 12 we're going to move on to in a couple weeks after spring break to move on to static equilibrium.